Oh my goodness. Oh my goodness. Oh shoot. I just woke up. Oh my gosh. Sorry guys. I just woke up. Mhm. So, okay. So, we'll get started with Madison's questions because she has her quiz this upcoming Friday. How are you feeling about that so far, Madison?
I'm nervous.
Yeah, it's a lot
It's
for
so
sure.
much.
Yeah, I know. Did she finish lecturing material?
Yes.
That's good. Did she send a list of like what's gonna be on the test on the quiz this Friday?
No. It comes out on Wednesday.
Oh
You
no. Oh shoot.
She'll like do her lecture on Wednesday typically, but it's usually not on like whatever she lectures on Wednesday usually isn't on the quiz.
Mm-hmm.
But today we went over like reactions of linear sugars.
Mm-hmm. Reactions and linear sugars. Um, let's see. Can you post the updated lectures to the Google Drive so I could see like what she went over specifically so that we could like practice that?
Oh yeah.
Yeah.
Yeah, I'll do that right now.
Thank you. There's also like carbonyl practice worksheet that she posted on her Canvas. I don't know if you saw that, but it's like a list of like a lot of reactions with carbonyls.
Is it the one that
Um,
we used from last quiz too? It's like some stuff from last quiz and then like also some from this quiz. It's like half and half.
yeah,
Like there's
like the
like 20
big
of them.
worksheet. Um, that wait, I think there's way more than 20 of them. Let me see. Like reaction tutorial 8B. Like there's the one, the A B C D E F G, like all the way to like BI.
Yes,
Yes, that one, that one.
I know what you're
Yeah.
talking about.
That one. Chapter 12 and 13, practice problems. Like
Okay.
aldehydes, ketones, enols, like all of that. Know for sure for this upcoming quiz, like how to do that. It's a lot.
Okay.
Yes, I know, I know.
I'll look for the one right
Uh-huh.
now.
Okay, okay. And for 118B, Peyton, Crystal, is there any topics you guys wanted to go over today for office hours? Or Wiley, is there anything you wanted to go over for 128B?
Yeah, you just told
Uh-huh.
me the um let's see, the amine, the
Imine with the I.
hydrazine and hydrogens
Hydrazine,
and
hydrazone,
oxines.
and oxines.
Just all the
So
nitrogen stuff.
those are all the nitrogens, like what they are, or
Just like review. Like I only got like just like one example for each, so I don't know if you
uh-huh.
have more examples to show me, but
Yeah. So we don't work with like hydrazine, hydrazone chemistry a lot. Like the only time I've seen hydrazine, hydrazone, and oxine are in the Wolff-Kishner reduction
okay,
mechanism.
okay,
Um, reduction mechanism. Yeah, like that's why we say hydrazine, hydrazone a lot, and hydrazone a lot. It's with the Wolff-Kishner reduction mechanism. So let me,
can you just go over amines then?
yeah, let's go over imines.
All right.
Yeah. Okay, so imines with the I, right? This is good for 118B and 8B as well. Um, is going to be a carbon double bond nitrogen, right? And this carbon here could be attached to two different R groups. We don't know what they are. And this nitrogen here is going to be neutral. And to be neutral, it has to be attached to a hydrogen or it has to be attached to an R group. Like that. Right, so that is an imine. A carbonyl is a carbon double bond oxygen. Like that. That's a carbonyl. You might see this as a acyl group. Now, we could convert a carbonyl into an imine, and it is reversible. Right? If we want to get the imine with the hydrogen right there, we could use NH3 in some sort of acid source. Right? It depends on the professor though. Like, what reagent does BO give you to form imine? Like some.
He just tells us to use just like he writes H plus and then below it pH 5.
Yeah. So like some imine pH 5, some acid source. Right? If you use ammonia, like NH3, then we're gonna get this imine with the one hydrogen on the nitrogen. But if we use a primary amine, right? And let's say that's R prime NH2 with pH 5. We're gonna get this imine here, where this nitrogen is attached to the R prime of the primary amine.
Okay.
Now I'm gonna show you the mechanism of the one with the primary amine, but it's the exact same as the one with the ammonia, right? It's just instead of an R prime, it's gonna be a hydrogen. So it's the exact same mechanism here. So this carbonyl carbon here, right, is electrophilic. Like there's a partial positive charge there. And this amine here is nucleophilic because it has that pair of electrons there. But consider this right now as a weak electrophile and this neutral amine as a weak nucleophile as well. So because they are both weak, right? Weak nucleophile, weak electrophile, this amine here cannot attack that carbonyl carbon right away. Like this will not happen. What we gotta do first is that we gotta activate the electrophile. We gotta make the electrophile stronger by protonating in the acidic environment that we are in at a pH of 5. Right? We have like protons floating around. And that could be in the form of like H3O plus, H2SO4, but some proton source that would protonate the carbonyl oxygen. Right? Once we do that, we're gonna get this intermediate here where this carbonyl is protonated and the oxygen has a positive charge. The result of this, right? Because the oxygen is positively charged, it's very angry now. It's very unstable now. So it's gonna want to withdraw or pull on the electrons of this carbon even more, making this carbon even a bigger positive charge. Right? So this right here is an activated electrophile now. It's a stronger electrophile. And because that carbon is a bigger positive charge now, the weak nucleophile is now able to attack the stronger electrophile. Right? And when we try to make a new bond between this carbon and nitrogen right there, we're going to break the octet rule for that carbon. So to conserve the octet rule, we pop that double bond onto the oxygen. So the two electrons in this bond right here will pop onto that oxygen, making it neutral again. So that's going to give us this intermediate right here. We have a single bond OH now, where this oxygen, before it had two pairs of electrons, it now has, before it had one pair of electrons, but now it has two pairs of electrons. It gained that second pair from this bond right here. And it's now neutral, right? We neutralized it. And now, this is the new bond that we formed right here. New bond between the carbonyl carbon and this nitrogen of the amine that we used to attack that carbonyl carbon right there, right? But everything else that is attached to this nitrogen, right? Like if I highlight it in yellow like that highlighted yellow nitrogen right there, everything else that is attached to it follows it as well. So that nitrogen right there is attached to two hydrogens and an R prime group, right? It does not have a pair of electrons anymore because it used that pair of electrons to make that new bond between the nitrogen and carbon right there. So the formal charge of this nitrogen here with 4 bonds and no pairs of electrons would be positively charged. Okay. Now this next step here, it depends on how the professor works. Levens, she deprotonates the nitrogen and protonates the OH at the same time. But I know some professors like Nasiri does not like to do that. Like they like to do it one at a time. Like deprotonate this first and then protonate this after. For Biot's mechanism, what does he tend to do? Like does he
You
kill
take
two
your
birds with one
NH,
stone?
your RNH2, and you deprotonate it.
Okay. So
It's your original starting material.
right. Our original starting material here is an excess, right? We're gonna bring that in a second equivalent of that to act as a base. Our end goal here, because we want to keep the nitrogen in the molecule, because our end goal is to get the imine here, we want to keep this group and we want to get rid of this group, right? But right now, this group is the good leaving group, right? Because it's positively charged and we could just kick it out right away. And this group is the bad leaving group. So we got to reverse that somehow. We got to convert this good leaving group into the bad leaving group because we want to keep it. So to make it into the bad leaving group, we got to neutralize it by deprotonating it with the base that we have, which is the starting material.
Yeah.
Right? So after that, we're going to get this neutral NHR prime. This is now a bad leaving group, and that's good. We want it to stay as a bad leaving group because we want to keep that nitrogen group. Now we want to get rid of this OH here, so we gotta first convert it into a good leaving group by protonating it with the acid source we have, right? Which is the pH 5, or we could use the protonated amine that we just protonated previously here, the R prime NH3 plus now. Right, so this is another proton source that we can have. This OH could get protonated by that and get converted into OH2 plus good leaving group. Now, once we have that good leaving group present, we could form that iminium ion, that carbon double bond nitrogen, and then kick out the leaving group at the same time, which gives us water as a side product. Right? And the reason why I call this an iminium ion is because this carbon double bond nitrogen here is positively charged. So it's an ion, right? Because it has a full charge there, which is called an iminium ion. Iminium ion. And this right here is an imine, the neutral imine. If this was mechanism, I would also draw out the water just in case for full credit to show all the side products. Now the last step here is to deprotonate that iminium ion into the neutral imine by using another starting material base to deprotonate it and make it neutral like that. Okay.
Alright, can you zoom out?
Yep. Did he also go over the reverse mechanism on how to convert the imine back into the carbonyl with water and acid?
I think he mentioned it, but never.
Okay.
Yeah.
Yeah. So it's like very like similar mechanism. Let's say we have this imine here, and we want to convert it back to the carbonyl, carbon double bond oxygen. What we want to do is use water and acidic conditions, the pH 5. So same exact thing. This water here cannot attack the imine right away because this is a weak electrophile. This is a weak nucleophile. We gotta activate the electrophile first by protonating it with the acid source and give us our stronger electrophile. Once we have this point here, the water is now then attracted to this strong electrophile, push the iminium bond onto the nitrogen that's positively charged, and give us this intermediate here. Okay, and our end goal here is this carbonyl, carbon double bond oxygen. So we want to keep this group, which right now is a good leaving group, and we want to kick out this group, which right now is a bad leaving group. So we gotta convert this into a bad leaving group first by deprotonating it with the water that we have to make it neutral and a bad leaving group. And we want to convert this bad leaving group with the nitrogen into a good leaving group by protonating it. And we can use H2O plus because we just formed that in the last step. When water grabbed this hydrogen, it becomes H2O plus, which can be used in the next step to protonate this amine and convert it into this good leaving group here. Okay, now once we have that good leaving group, we could drive it off by forming the carbonyl bond, carbon double bond oxygen there, and kicking out that whole group, which gives us our primary amine back, R prime NH2, and this carbonyl, which this oxygen still has its hydrogen attached to it, right? So that's why it's positively charged. And the last step is to deprotonate it. You can use water or this amine as a base to grab that hydrogen and deprotonate that carbonyl to give us our neutral answer there. Like that. Okay. So that's imine formation forward reaction. And then if you want to do like hydrolysis of imine, right? This right here is called hydrolysis of imine. That converts the imine back into the carbonyl with water in acidic conditions. Hydrolysis. Right. Okay. Let me check Madison's folder for 8B.
I think I texted you the images as well, or like what related as well.
Yeah.
I thought it's easier. I don't know.
Yeah, let me get my phone really quick. I'll be right back. Okay. Drawing carbohydrates, cyclizing monosaccharides from Fischer projections. Tip center, molecule exposed to coral. Okay, decide you're making 5 membrane, Furnos or 6 membrane. Oh yeah, she made a procedure of this, so that's good. Count the number, rotate, nucleophilic iso addition, number of atoms, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And then she rotated it like that. Interesting.
I'm like halfway understanding how to do that and halfway like not understanding.
Yeah. So the way that she does it
Very
is different than how I do it, but let's do it her way. Well, actually, no, let's do it my way first, and then I'll show you her way, how she did it afterwards, because it's basically the same thing.
Okay.
Right, the cyclized sugar as alpha and beta are mixed anomers, the carbons with the ring. So arseners, ketoses, wicked, but carry an argon rather than the aldehyde at the NR carbon. Okay. Let me show you here. Oh yeah. Someone asked what drink was I drinking earlier. This is coconut water. Coconut water from Costco. Oh, I usually get the other one. What was it called? Harmless Harvest. But I'm trying out this one this time. So carbohydrates or sugars, its linear form is gonna be represented as a Fisher projection. And that's gonna be some 8A stuff. Remember that, Madison? Or like from your community college, did you go over Fisher projections, like this weird looking fishbone looking structure?
Yeah, like briefly. I just
Uh-huh.
remember like the basic stuff of it.
Mm-hmm. Yeah. Um, well, there's two different carbohydrates that I want you to know about. There's aldoses and ketoses.
Yes, I think
Yeah.
that's what she like focused on.
Mm-hmm. Aldoses, think of it as aldehydes. Ketoses, think of them as ketones. Aldehydes, ketoses, ketones. Okay, so an aldehyde, think of it as CHO. When you see CHO in the Fisher projection, you think of, so let me just write that squiggly line to show that it's attached to something. This aldehyde right here, and that's the CHO, the CHO, right? The C is right here, the H
Mm-hmm.
is right there, the O is right there. That's the CHO right there. Okay. Now, I'm going to give you a common CHO right here, which is D-glucose. And she wants you to memorize like 4 or 5 sugars, right? D-glucose, D-fructose, D-ribose, D-glyceraldehyde, like those things right there. You could put that in your
Yeah.
note card, right?
Glucose, fructose, ribose, and glyceraldehyde.
Glyceraldehyde, yes. Uh-huh.
Yes.
Right. And that's the smallest one, the 3-carbon sugar, glyceraldehyde. So there is a trick that I use to memorize the glucose. So let's try this. Use your right hand, right?
Uh-huh.
And these 4 horizontal lines right here are gonna be your fingers. Okay?
Okay.
Where the alcohol points to is the direction of your finger. So this is your index finger, this is your middle finger, this is your ring finger, this is your pinky finger. Okay? So index finger is gonna go to the right, middle finger goes to the left, index and ring finger goes to the right, like that.
So you're wait. So you're flipping somebody off.
Yes. Does that make sense? Like where my finger goes to is where the alcohol goes to. Like the first
Okay.
finger here is to the right, second finger, the middle finger is to the left because the alcohol here is to the left, and then the index and ring and pinky finger, alcohol goes to the right, like that.
Okay.
I'm not flipping you off, okay? This is just the
No, you got it. You got it. I know what you mean.
Yeah, so but actually when you try this on the exam, be careful because like your TA or the professor might see you do that and they might think you're flipping them off or something. Yeah.
Right.
Uh-huh.
Yeah, that
Now
makes
that's
sense because
D-glucose.
all your
And
fingers.
D-glucose is what we call a specific type of D-aldohexose. Okay, so let's break that down. Aldo comes from the aldose part. We see the CHO there, so that's the aldo part, aldose. Hexose, that's 6 carbons long. For hex, like hexane, hexagon. Hexose, 6 carbons long, which is this 1, 2, 3, 4, 5, 6 carbon long carbohydrate like that. Like each point here in the Fisher projection is a carbon.
Right.
And the D sugar here comes from the last chiral center, which is this carbon right here. If the alcohol is on the right side, then that's a D sugar. Right? If the alcohol was on the left side right here, OH, and the hydrogen was on the right side right here, that would be an L sugar. If OH on left side instead, then that would be considered an L sugar. Like that. Okay? And it has to be this last chiral center here. It cannot be this carbon because that's the first chiral center. This is the second chiral center, third chiral center. And this is the last chiral center because this carbon here is not a chiral center. That carbon there has 2 hydrogens, right? Because of the H2. And because it has 2 of the same groups, it's not a chiral center. Right? That is the last carbon of the structure, but it's not a chiral center, so we don't consider that as the last chiral center. This right here is the last chiral center right there. Okay. Now, D-fructose, on the other hand, is a D-ketohexose. And so we know that this is going to be ketose because of the keto part. And that's going to look like this. The top carbon is going to be a CH2OH primary alcohol, as well as the bottom carbon. So both top and bottom carbons are CH2OHs.
And why are they CH2Hs again?
Yes, we want them to be CH2OHs because the bottom part is always going to be CH2OH for both aldose and ketoses.
Oh,
For
they are. Okay.
carbohydrates, right? The difference between aldose and ketose is the top two carbons, right? The top two carbons, the aldehyde here is a CHO, which is the aldehyde part, which looks like this, the aldehyde functional group right here, right? Where we have a hydrogen at the end. It's at the terminal end of the molecule. But if you think of ketone for ketose, the ketone is not at the end of the chain, right? It's a ketone
Right.
is like the carbonyl is in between two R groups, two hydrocarbon chains, 2 random groups like that, right? So this carbon double bond oxygen right here has to be like at the second carbon, which is in between this R group and all the other R groups right here, like that.
Right. Okay.
So that's gonna be the case for all the ketose, for all ketoses. The carbonyl is always at the second carbon for all ketoses. Okay. And D-fructose would copy and paste everything else like D-glucose is, like that, like that, like that. H and H. Okay. So I'm gonna close the ring for D-aldose first, and then close the ring for D-ketose after.
Okay.
So this right here is my D-glucose. 1, 2, 3, 4. OH, 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 HH. Okay, and I'm gonna redraw that like this, where the CHO is gonna be expanded out to show out that functional group more clearly. 2, 3, 4. H, OH. So okay. Let's say we want to make a 6-membered ring by closing the ring here. This carbonyl carbon, the carbon double bond oxygen carbon right there, is our electrophile because it is partial positively charged since it's attached to this double bond oxygen here, right? All of these other carbons here are also partial positive charge, right? Because they're also attached to oxygens, but they're not the electrophile because there's no leaving group there, right? These OHs here are terrible leaving groups, right? They're bad leaving groups. Whereas this carbonyl carbon right here has like a good leaving group because when a nucleophile attacks it, like let's say some kind of nucleophile attacks it, we could pop that double bond onto the oxygen like that as a leaving group.
Right.
Right. And so the way that I do this is that I number my number 1 atom, the carbonyl carbon, right? When I close the ring.
Right.
And if I want to make a 6-membered ring, I'm gonna keep going down until my 6th atom here is my nucleophile. So 1, 2, 3, 4, 5. This carbon here cannot be my 6th atom because that carbon is not the nucleophile. It cannot attack that carbon one there. There's no electrons on this carbon like that we could use to attack that carbon right there. Right? So we gotta either go to the right or to the left. We're gonna choose to go to the right here, where this oxygen is my number 6 atom because that oxygen has 2 pairs of electrons that it could use. Like 1 pair of electrons can be used to attack that neocarbon right there. So does that numbering system make sense? This is not for nomenclature, by the way. Like when you name these, like this is not for nomenclature. This is just my system of how I close the ring right here. Right?
Yeah. No,
Now,
it totally makes sense.
Yeah, that's good. You notice how the number system here is going straight down and then at the very end it like tilts to the right? We don't want that. That's bad. We gotta do something else before we close the ring. We gotta rotate them so our numbering system goes straight down. Right? And I'm gonna rotate them like this. I'm gonna rotate this alcohol, this H2OH, and this hydrogen around. Right? Because I'm gonna keep this bond stationary. Like imagine holding that bond with your hand and you're rotating these 3 groups around, where I'm gonna rotate the alcohol to the bottom. The CH2OH is forced to go to where the H was, and the H is gonna go to where the OH was, like that. So we're just rotating those 3 groups around like that. Everything else on top stays the same. It stays stationary. Okay? So as a result, I'm just gonna draw out that last chiral center. OH is on the bottom. CH2OH is on the left. And then hydrogen is on the right, like that. That's the result of this rotation of the 3 groups right there. Where this carbon here is carbon 5, right? That's carbon here is carbon 5 right there,
Yeah, that makes sense.
right? Everything else is copy and paste now. Like nothing changed to the other carbons, so we just copy and paste everything else. 1, 2, 3, 4. Like that. OH, 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 H, H, H. This is 1, this is 2, 3, 4, 5, 6. Now this is good. This is perfect. Our number system is going straight down, like that. Okay. So we can proceed with the procedure now. Imagine this vertical bond here is my arm, and I'm gonna topple it 90 degrees clockwise. Like I'm gonna tilt it overwards, like cutting a tree and it timbers down clockwise. That's gonna be this right here, where that's 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, and atom 6 is that oxygen right there. Let's look at atom 2 and focus on the alcohol right here. If I timber the tree clockwise this way, would the alcohol be on the top side or the bottom side? If the orientation of the alcohol is on the right side right here.
It would be on the top side.
So let's think about this. Like, let's say this is my arm right here, right? And the alcohol is on my right side right here. And I make it timber go clockwise like that. It's gonna go down. It's gonna face down. Right?
Alcohol.
Because the alcohol,
So
like on carbon 2.
You're tilting. So from it being straight up and vertical, you're tilting right.
Yes, we're tilting right to make it horizontal. Like this whole thing is gonna be horizontal. Like
Does
if
it always tilt right then?
Yes, always tilt it to the right when you're closing the ring. Do not tilt to the left. If you tilt to the left, then your alcohol on carbon 2 would go up, right? Like if you make it go to the left, like counterclockwise.
If you tilt it to the right, why isn't the carbonyl on the top then?
Oh yes, so the carbonyl, like if it's easier to see, the carbonyl can be on the top
Does
as
it
well.
matter?
When we close the ring, it does not matter because what matters here is the orientation of the chiral centers in the center, right in the middle. Because in the final product, that's what determines our wedges and dashes in the sugar or our axial and equatorial bonds. What goes up and what goes down. You're gonna see that eventually this carbonyl right here, when it gets attacked by something, you know how that is an sp2 carbon that's flat and planar. When it gets attacked, it could get attacked on the top side or bottom side equally. Pops the bonds to oxygen, so we could get a wedge or dash product here. And this carbon, because of that, we get 2 different anomers as a product. And which is why that carbon there is called the anomeric carbon. Does that sound familiar, that term, anomeric carbon, anomers?
Somewhat, yes.
Right. Okay. So, it doesn't matter where the carbonyl is here, but if you want to think of it like that, the carbonyl should be facing up if we timber it to the right, clockwise like that.
Okay.
Okay. Now, carbon 2, alcohol is going to go down. Carbon 3, where's the alcohol going to go?
On the top.
On the top.
And then on the bottom. And then the CH2OH is on the top. Yes.
So you can think of it like everything on the right side here is down, everything on the left side here is up. Right. This just helps you visualize why that's the case.
Yeah.
Okay. Now, this is when we do the nucleophilic acyl addition. This oxygen here that we labeled number 6 is going to use one of its pairs of electrons to attack this anomeric carbon, this sp2 carbon right here, which would pop this double bond onto oxygen like that. And we know that that's going to make a 6-membered ring. And we're going to draw that 6-membered ring out like this as a base template in Haworth projection first. Where this is atom 1, this is atom 2, atom 3, atom 4, atom 5, atom 6. like that. So this is, if I highlight that whole thing in yellow right there, that backbone yellow comes from this backbone yellow structure right there. Oh wait, is my Zoom lagging? It's like I think it's delayed. It's not showing up to date.
I think it's like kind of going in and out of it, but it's going like I can see the screen. The screen I feel like is fine.
Right.
Just
I see
your
it,
video might be.
Right. Was I cutting off earlier?
Yes, I can
Oh
hear.
shoot, I think my Wi-Fi is like bad. Let me turn off my Wi-Fi so it's better really quick. So what about now? Is it better now? Hello?
Yeah, I can hear you.
Okay. So now carbon 2, we see the alcohol is going down. Carbon 3, alcohol is going up. Carbon 4, alcohol is going down. Carbon 5, CH2OH is going up. And we could draw that out as CH2OH, or we could draw it out like this, where this is the CH2 right here. Right? This oxygen 6 right here had a hydrogen. So before, its intermediate had that hydrogen and a positive charge, but when we close the ring, just get rid of that hydrogen to make it neutral, right? And we don't have to draw that out.
So
Now,
2, the OH is down, just like the Fisher projection. And
like
then
that.
like 3, the OH is up.
And
then 4, the OH is down.
Right.
And then 5, the CH2OH is up.
Yes.
That's what you're talking about? Okay.
Yes. I saved carbon 1 for last because when we pop that double bond to the oxygen, it becomes OH, but it could go up or it could go down, giving us 2 different products. Right? And these 2 different products are anomers of each other. There's an alpha anomer and a beta anomer. Now, let me just make sure which anomer is what, just to make sure before I give you what anomer is what. Okay, so this is gonna be the alpha anomer, and this is gonna be the beta anomer, and I'll show you how I determine that.
These make sense to me.
Like the process, like how we close the ring here. That's good. That's good.
Like pretty.
It's basically like that what she did on the paper.
Yeah.
It gets more difficult with the ketose because you can make a 5 or 6 member ring, but we'll go over that tomorrow because I want to go over some 118B stuff at the end.
100%.
Right. Now this right here is the anomeric carbon, right? The first carbon that had the carbonyl carbon that was attacked, right? Because that anomeric carbon leads to 2 different anomers, the beta anomer and the alpha anomer. Right. Circle the anomeric alcohol, which is that anomeric alcohol right there, and look at the CH2OH at carbon 5, the carbon on the other end of the structure, like that. Notice how these 2 are cis to each other, they're both going up. If they're cis to each other, then that gives a beta anomer. If they are trans to each other, then that's the alpha anomer. We see that this alcohol is going down, this H2OH is going up. So because they're trans to each other, that's the alpha anomer. So that's how we classify the difference between an alpha anomer and a beta anomer.
Okay, that makes sense.
Yeah. So that's closing the ring, what an anomeric carbon is, what the 2 different anomers are, how to determine them. For D-glucose, tomorrow we'll do for D-fructose because there's like, you could form a 5-membered ring like that, or you could form a 6-membered ring like that for D-ketosis, for ketosis.
Okay, but it's the same process, correct?
It's the same process, correct. But the D-ketose one, or like the ketose closing one, if you make a 5-membered ring, there's an extra step that is kind of sneaky. But it's the exact same step. Like, you're just gonna worry about that one step, which I'll go over tomorrow.
Okay, perfect.
But I'm gonna give you practice here.
Okay.
Right? Oh yeah, this is the Howard projection. You could also convert this into this little guys. Right? Where this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the axial bonds are up, down, up, down. That's up, down. Equatorial bonds are going to be this, opposite to the axial bonds. So at carbon 2 right here. Oh, wait, no, that's atom 6. I numbered this incorrectly. Right? This is 1. That's 2. That's 3. That's 4. This is 5. This is 6. I numbered this incorrectly. This is 1. This is 2. This is 3. That's 4. That's 5. That's 6. Now at 1, if we draw the beta enantiomer, alcohol is going up, which is equatorial. Carbon 2, alcohol is down, which is equatorial. 3, up, which is equatorial. And you're going to notice that D-glucose, right? Some people call it the all-equatorial sugar because the alcohols in the chair conformation, the alcohols are all in the equatorial position, right? It's going to be different for all sugars, but the reason why D-glucose is all equatorial is because the alcohols like match up with the like whatever we had here, right?
Right.
Because equatorial is going up, axial is going down, so you got to just match that. For the alpha, for the beta enantiomer especially.
Okay, that makes sense.
Right. It's different for the alpha enantiomer because the only difference is the carbon 1. Right? Everything else is the same. OH there, OH here, OH here, OH here, H here. But at the enantiomer carbon 1 right here, our alcohol is going down. And the bond that's going down is axial. Right there. Right? So that's the difference between this alpha enantiomer and beta enantiomer. At the enantiomer carbon right there. Like that. Okay. So just for practice, I want you to close this ring. And you can show me tomorrow or text me when you have it. Into both the alpha beta enantiomer, draw both the Haworth projection and the chair conformation.
Oh gosh. Okay.
It's the same exact process as what I just did, but the alcohols are going to be in different locations now. Right, and this time it's going to be an L-glucose. Oh, I mean, not L-glucose. This is not glucose. L-aldose. Right, this is an L-aldo hexose.
Do you think she'll test like this should be on like the quiz and stuff? Or more into depth about this?
I think so. She went over this today?
I think she went over the closing of the rings today, but she went over like the basic like glucose, fructose, like all the sugars a couple days ago.
Oh yeah, so all the basic stuff, like classification, is gonna be on the quiz for sure. Like how to identify if it's L-aldo hexose or L-aldo pentose or L-aldo tetrose or keto hexose. Like those classifications, D sugar, L sugar, dextrorotary, laboratory, like those conceptual stuff and how to classify them is gonna be there for sure. But the ring closing stuff, I'm not sure because she just went over that today. But it might.
Okay.
I'll have to see the list when she sends it. Send me the list when she sends it.
Okay.
Okay. So here's your homework, Madison. Close the ring. Give me the alpha beta enantiomer in the Haworth projection here and the chair conformer here. Both alpha and beta enantiomer.
Okay. Thank you.
Yes, of course. Okay, Peyton, Crystal, is there any 118B concepts you want to go over, like Diels-Alder, electrocyclic ring opening, closing, EAS, directing group EDG, EWG, orthopara-director, meta-director?
Can you please go over pericyclic?
Yes.
There's these reactions from our post lab, and I was wondering if you can go over them.
Yes, of course. You could message me on school, or I'm gonna DM you my number. You could text me.
Okay.
And I could look at it.
Okay. That's cool.
There we go.
I already sent it in
school. Okay, let me check. I see it. Okay. Okay, so these four here, Diels-Alder. We have this diene and this dienophile with the two EWGs, CF3 and CN. And we have heat with it. Now, I'm going to highlight the diene part, which is that in yellow, and the dienophile part, which is that in blue right there. I'm gonna draw the pocket between the diene and dienophile like that. Then I'm gonna see if, well, before I do that though, there was something else I did, but I didn't verbalize it. I had to see if the charge is aligned for redrochemistry, right? And they do, because this is an EWG, this is an EWG. So when we withdraw electrons from this EWG right there, partial positive charge up there. When we withdraw electrons from this EWG, partial positive charge down here. And these two are EDGs, giving negative charges on both carbons as well. So there's negative charges and positive charges on both sides of the diene and dienophile, so the charges do align, so we don't have to worry about flipping anything or rotating anything, right? So if that's the case, then I draw out the pocket between the diene and dienophile, right? So for Diels-Alder reactions, before I draw the pocket between the diene and dienophile, I see if my charges align or not, right? Based on the EDG and EWG. Then after that, I determine my out and in groups. These are my out groups. These are my in groups because they're inside of the pocket. And these are my EWGs. Right? And based on the endo rule, the out group is cis to the EWG, the in group is trans to the EWG, based on the endo rule. So when I draw out the base template of the products right here, right, where if I number them like this, 1, 2, 3, 4, 5, 6, that's going to be this numbering system right here. 1, 2, 3, 4, 5, 6. So this product here is always going to be there for all Diels-Alder reactions. Everything else is decoration. If I decide to make the out groups dash, like this dash isopropyl here, this dash methyl here, the EWGs here, this dienophile here is cis, so we got to make them cis to each other, right? And they're going to be dashes as well, because we want the EWGs to be cis to the out group. If the out group is dash, then the EWG would also have to be dash, like that. The in group here is going to be wedge, right? And because they're fusing 1 and 2 together, I'm drawing it like this, right? If that bond was not there, and then the in group was just like that, not connected to each other, then I would draw out the methyl groups like that for the in groups. But because they're fusing together, that's making another ring right there. And another way that you could visualize this is this structure right here, like that. Where this is the isopropyl, methyl, this is going to be the CN, this is going to be the CF3 right there. So that's just another way of visualizing what the structure is. And that's going to be this atom 1, 2, 3, 4, 5, 6, like that. Right? So that's one of the products, plus minus. We're going to get another product as well, which is going to be this structure here, where the CF3 is on top, the CN is on bottom. And what I did to get that product was I just flipped the dienophile upside down. And the reason why I was able to do that is because we have partial positive charges equally on both sides, partial negative charges equally on both sides. So we could have done the same reaction, but we flipped the dienophile upside down where the CF3 is on top this time, and the CN was on bottom to give us this set of enantiomers instead. So we get 4 products. This set of enantiomers and this set of enantiomers right there. Any questions on that one? Yes, the bridge could have been a dash, but that would have made all of these wedges, right? And then the bridge would be like down here, and then all of these groups would be up here instead. And that's the enantiomer of that. Right. Okay. Okay. So, when is this post lab due?
It's due. I'm sorry. I think I accidentally turned on the echo.
Oh, it's
It's
okay.
due on. Sorry, it's due on Wednesday.
It's due on Wednesday. Okay, I will go over the rest tomorrow, but I want you to like try out the rest based on what I went over here today, and then I will check your work tomorrow so that you have a chance of practicing these. Okay, sounds good.
It sounds good.
That's good. That's good. Are you at the library right now, or with Peyton?
I'm at the Assisi.
I see. I see. Okay. Okay. Yeah. So yeah, we'll do more 8B practice medicine for tomorrow with the brain closing and carbohydrate practice for your quiz, and finish off this for 118B, guys. Okay, that's good. Okay. So good night, guys, and I hope you guys have a nice night. Yeah. See ya.